And now for something completely different. What we're going to do now is we're going to begin looking at different ways we can look at a signal. All the things that we learned before, all those classifications and stuff, we are going to forget all about that, except for one thing, the idea of a linear time invariant system. And that's what we're going to use to define the way we're going to look at signals. Okay, and the other thing we will need is, of course, something that you will never, ever, ever forget, and that's Euler's law. So here's the idea. Suppose I have a signal, and let's make it a very weird signal or a very simple signal to start with. Let's suppose I have signals which are always constant over an interval of an integer. So maybe it's 1 from 0 to 1, and then 2 from 1 to 2, and then minus 0.5 from 2 to 3, and then 0.5 from 3 to 4, and so on. So it's always constant over a period of an interval of 1 unit. Okay, and then it changes, and it can take on whatever value it wants. So here's the kind of signals that I'm looking at, and this is the world in which I live in which all signals are of this form. So if that's the case, I can come up with a signal, let's call it B of t, and B of t is 1 from 0 to 1, and it's 0 everywhere else. And what I can do is I can take any x of t, which is of this form, and I can write it in terms of B of t. So for example, this particular one, I could write this one as 1 times B of t plus, this say is a height of 2, so this is 2 times b shifted by 1 plus or minus 0.5, so plus minus 0.5 b of t minus 2 plus 0.5 b of t minus 3, and you can see how this goes. I can keep going like that, right? And now if I make a definition, let's call b sub k of t to be equal to b of t minus k, then I could write x of t as 1 times b1 of t plus, or b0 of t plus 2 times b1 of t plus minus 0.5 times b3 of t, and so on. b2 of t. Keep wanting to go one step too far. Okay, or I can make this general rule. I can say any function which is of this form can be written as summation a sub k b sub k of t. Right? Where in this case, a0 is 1, a1 is 2, a2 is minus 0.5, and a3 is 0.5. I can then say, well, you know, if I want to know what ak is, all I have to do is I'll take x of t and I'll multiply it with bk of t, and I'll integrate it. And I'll let the integral be from minus infinity to infinity, and that'll give me what ak is, right? Because let's suppose I wanted to find what a0 was. If I wanted to find what a0 was, which is 1 in this case, I would take x of t and multiply it with b of t, and that would give me 1 times b of t, and the rest of it would be 0. And when I took the integral of that, I'd just get 1. If I wanted a2, I could take x of t and multiply it with, a1, I could take x of t and multiply it with b of t shifted by 1, and that would give me a rectangle of height 2, and if I took the integral of that, I would get 2, and so on, right? I've got all of this in the notes in much more detail so you can take a look. So what does this do? It allows us a different way of looking at functions in this world of ours in which we only have these simple functions, right? Instead of writing or drawing x of t like this, or even writing it like this, we could just, for example, let's limit ourselves to just, 1, 2, 3, 4 time units, right? So let's suppose all of our signals are just 4 seconds long. In this case, I could take any of these signals and I could just write them as a vector. For example, this one would just be 1, 2, minus 0.5, and 0.5. And this vector of the coefficients a sub k would represent this signal. And once I have a vector, then I can do all the things that you can do with vectors. I can take inner products, I can take, I can rotate it, I can do all kinds of different things that would be kind of difficult to do if I just had to deal with the function x of t. So having an alternative way of looking at something allows me a lot of flexibility in terms of what I can do with that. And that's kind of what we're going to do, is we're going to try to find out an alternative way of looking at signals, right? And what I'm going to be using is going to be a set of basis functions. So if this is my set here, if I look at this set, the set b sub k of t, I can call this set my basis function that leads me to this set of coefficients, right? So these are my basis functions. This is the set of coefficients. What I would like to have is a set of basis functions that don't just allow me to represent these very simple functions in my very simple world, but all of the functions that I'm interested in. And are there such functions? Yes, there are. There are many such functions that will allow you, if you use them as a basis set, they'll allow you to represent all particular functions of interest to you. But I want to go one step further. I want to have a basis set that allows me to take linear time invariant systems and let me deal with the relationship between the input and the output of linear time invariant systems in a way that is more convenient than what I have right now. What I have right now is I can take the function and I can convolve it with the impulse response and I can get the output, right? But this is, as you might have noticed, is complicated. And it's complicated even for the very simple functions that we've been using. Up till now, we've been dealing with unit step functions and we're with decaying exponentials or pulses. All of these are very simple little functions. But what we want to deal with is signals that are much more complicated. Signals like, speech, the way we're talking, or music, which is much more complicated, or video or images or all of these things that really would be difficult to represent with just square pulses and decaying exponentials. So what we want is a basis set that will represent all of these functions. The question is, of course, are there such basis sets? And the answer, like I said, there are many such basis sets. And what I want to do is I want to be able to use the basis set that I have in a way that will allow me to relate the input and the output of a linear time invariant system without the use of this complicated convolution integral. Okay? And the basis set that will allow me to do it is our old friend, e to the j omega t. And in order to see that, let's take e to the j omega t and let us put it through a linear time invariant system with impulse response h of t, and let's take a look at what y of t looks like. Okay, so in this case, y of t is equal to integral from minus infinity to infinity of x of t minus tau, h of tau d tau, and that's going to be equal to integral from minus infinity to infinity of e to the j omega t minus tau, right? That was my x, h of tau d tau. And that's going to be equal to, let me split this up. So this is from minus infinity to infinity, e to the j omega t, e to the minus j omega tau, h of tau d tau. Or I can write that as e to the j omega t, integral from minus infinity to infinity, h of tau e to the minus j omega tau d tau. Okay, let's take a look at this integral. This integral is dependent only on the impulse response. So given a particular impulse response, I can find this integral, I can solve for this integral for a generic value of omega, right? And then when I do that, I'll be left with, I'll integrate out the variable tau, I'll be left with some function of omega, and I'll call that capital H of omega. Okay, so here's my input. My input was e to the j omega t into this system, and my output out of this system is again e to the j omega t, and then h evaluated at this omega. Right? At this omega is kind of important, because now what I can do is, if I put in e to the j omega 1t, then the output will be e to the j omega 1t, h evaluated at omega 1. If I put in e to the j omega 2t, then my output will be e to the j omega 2t, h evaluated at omega 2, and so on. Right? So if now, as I claimed, these can be used as a basis set so that I can generate signals of the form a1 e to the j omega 1t plus a2 e to the j omega 2t, and then I immediately, given this, I know immediately what the output is. The output is a1 e to the j omega 1t, h of omega 1, plus a2 e to the j omega 2t, h of omega 2, and that's it. I don't have to do convolution. I don't have to take any integrals. All I need is this function, and I need these coefficients corresponding to each of these frequencies, right? But can I do that? Is this, I mean, this looks kind of weird. I mean, these are sum of two complex exponentials. Can I take signals of interest to me, actual real signals, like a speech signal, and can I write it in terms just of omega? The answer, in the immortal words of Dolores Huerta, is yes, we can. And that's what we're going to do. So that's pretty much what we're going to do from here until your next test, is we're going to take different kinds of signal, and we'll show how we can represent those signals in terms of omega. Right? We'll start out with very simple signals. We'll start out just with periodic signals, and we'll show how to represent periodic signals in terms of omega, and then we'll take more complex signals, general time functions, and we'll see how we can represent those in terms of omega. And then we'll kind of go back one step and look at discrete signals and see how we can represent those in terms of omega. Okay, and this whole area is called Fourier analysis. It's called Fourier analysis is because Joseph Fourier kind of, used this method to look at several things of importance to him at that time. So he was working for some metallurgists, and he was looking at how to take metal and form it and heat it in furnaces and stuff. And so he wanted to figure out how the heat propagated through a bar of metal. And what he found was he could do that because he was looking at this heat signal that was propagating in the system, which was the ingot, the bar of metal. And he found that he could do that easily if he took the signal and broke it up in terms of this particular basis set, e to the j omega t. And because he used it a lot, we associate it with his name. He wasn't the first one to come up with it. He wasn't the one who popularized it really in terms of linear time invariant systems. But, to him who has a lot is given, and Fourier had a lot, and he was very famous, and this became associated with him. So it's called this whole area is called Fourier analysis. Okay, so let's take a look. Start out with really simple periodic signals. Okay, that's what we're going to start out with. So let's take a periodic signal, x of t, and remember what a periodic signal is. A periodic signal is one in which x of t is equal to x of t plus cap t. So the signal repeats itself every cap t seconds, and this cap t is called the period. The fundamental frequency of the signal is 1 over cap t in hertz. So this would be if I was using hertz. Or what we will use is the frequency in radians, which is just 2 pi times f naught. So it's 2 pi over cap t. And this will be radians per second. Okay, so the idea is that I can take any, and now from here on, I'll just be talking about periodic signals, okay? And here's this claim that I will make without any proof. And the claim is that given any periodic signal, I can write it as a sum of some coefficients times multiples of the fundamental frequency. Okay, so here is my fundamental frequency in radians. And what I can do is I can take e to the j times the fundamental frequency. Remember that e to the j omega t is just cosine omega t plus j sine omega t, right? So these are just sinusoids, complex sinusoids at this frequency. So I start out, I have a0 times e to the j0, so that's my DC coefficient. And then I have a1 times e to the j omega naught t, so that a1 corresponds to the fundamental frequency. And then I have a2 times e to the j 2 omega naught t, so that's my first harmonic, and so on, right? Except I also have negative values of frequency. So how do I have negative frequency values? Well, remember, I'm dealing with complex exponentials here, and what I want to end up with is real signals. And in order to do that, I need to have some way of, if I want a real signal, I need to get rid of the imaginary part somehow. And I'm going to do that by using this kind of construct, which is the negative frequency. It turns out that it's not going to be that much of a hassle, but this question keeps coming up as to what is a negative frequency. And really, it's more of a mathematical construct that we use in order to represent real signals using a complex basis set. And we like using the complex basis set because it allows us to relate inputs and outputs of linear time invariant systems. Okay, great. So we have this, and we are claiming that we can represent all periodic signals using this. How do we find these coefficients? In order to find these coefficients, we will use a very simple property or a relationship, which is this. If I take e to the j k omega naught t, and I multiply it with e to the minus j n omega naught t, and I integrate it over one period, and it doesn't matter which period you select, and then divide it by t, then this is equal to 1 when k is equal to n, and is 0 when k is not equal to n. Okay, this is very easy to obtain, and I've got it in the notes, and you can see it kind of easy too. So if I have 1 over t e to the j, I can combine these two. So this is k minus n omega naught t dt, right? When k is equal to n, then I'll just get the integral over one period of e to the power 0, which is just 1. So if I integrate from 0 to cap t, for example, this will be just cap t, and I'll divide cap t out, and I'll get 1. If k is not equal to n, then I'll have cosine of n omega naught t, or cosine of something of k minus n omega naught t, and sine of k minus n omega naught t, and I'll be integrating over one period, 0 to cap t, which, depending on the value of k minus n, might be several periods of the cosine and sine. And if you think about it, if I integrate cosine or sine over one period, here's a cosine. If I integrate it over one period, this area is equal to this area, and so the integral is going to be 0. If it's integrated over two periods, it doesn't matter. We get the same thing happening over and over again. So as long as we integrate over an integral number of periods, the integration is always 0. Okay, so the math I have in the notes. So take a look at that. Okay, now let's use this property to obtain these coefficients. Okay, so here's what I'm going to do. I'll take x of t and multiply it with e to the j minus j. Which one should I use? N? Okay, let's use n. Omega naught t, and then I'm going to integrate it like that. Okay, so then this is equal to, remember what x of t was. X of t was summation k equals minus infinity to infinity, a sub k e to the j k omega naught t. So this is going to be 1 over t integral, and I'll put in the definition of x. So that's k equals minus infinity to infinity, a sub k e to the j k omega naught t, and then I have e to the minus j n omega naught t dt. And then, moving this up, we get 1 over t integral. Let's take the summation and the integral and swap these, and then I can take a sub k and move it out of the integral as well. So I get summation k equals minus infinity to infinity, a sub k integral e to the j k omega naught t e to the minus j n omega naught t dt, which is equal to, let's make that 1 over t inside as well. So this is summation k equals minus infinity to infinity, a sub k, 1 over t, and I have e to the j k omega naught t e to the minus j n omega naught t. So and this we know is equal to 1 when k is equal to n, and 0 when k is not equal to n. So the summation is over all of k. So this entire term, because this is going to be 0 when k is not equal to n, so for all values of k not equal to n, we'll get 0 out of this. And so all those terms will be 0. The only term that's going to be non-zero is a term where n is equal to k, and for that, this whole thing is just going to be 1. So everything here is going to be 0 except for when k is equal to n. And when k is equal to n, this is going to be 1, and this is going to be a sub n. right? So I can find these coefficients. I can find all of the coefficients of my expansion. So here's my expansion. Here's the two equations that you need. My expansion itself, which is k equals minus infinity to infinity, a sub k e to the j k omega naught t. And in order to find these a sub k's, all I need to do is take the integral 1 over t over one period. So I'll just write it like this. X of t e to the minus j k omega naught t. So this k is the same as this k. Here I used n, so I got a sub n, right? I'm going to use k, so I'll get a sub k. That's it. That's the equation you need to get the coefficients, and once you have the coefficients, you can put them all together and you can get the periodic function. So let's do an example. Let's take a square wave. And let's make it even for now. And it goes like this. And it has a period t. So this is, then this will be t, and this will be minus t, and so on. And it has a pulse width of something, let's call it t0. So here's a periodic function. And according to my claim, and I'll actually show you that this is true. According to my claim is that I can write this as a sum of complex exponentials. And so I can write x of t as this sum. K equals minus infinity to infinity, a sub k e to the j k omega naught t. And now to find a sub k, I'm going to integrate over one period of this function. Okay. Now, the question is, which period should I pick? Should I pick from here to here, or should I pick from here to here? You know, I can go from minus t over 2 to t over 2, or I can go from 0 to t, or I can pick whatever interval I want. Okay, it doesn't matter. I'll get the same answer. So you pick the interval that makes it the most convenient for you. And in this case, the most convenient interval is from minus t over 2 to t over 2, because in this interval, I have this part which is 0 and this part which is 1. So all I have to do is just integrate from minus t0 to t0 of 1, and that's going to be a simple integral. Okay, so let's do that. So this is equal to, this is just x of t e to the minus j k omega naught t. And like I said, the integral is over one period. So I'm going to make this one period from minus t over 2 to t over 2. And so in this one, from minus t over 2 to t0, it's just 0. I don't have to worry about that. So then this will be from minus t0 to t0, x of t is just 1. And I have e to the minus j k omega naught t dt. And from t0 to t over 2, it's again 0. So I could write this. In fact, let me do that. And that way, you know, I could write it like this. So instead of going from minus t over 2 to t over 2, I can say from minus t over 2 to minus t0, x of t e to the minus j k omega naught t, plus the integral, let's make this outside, plus the integral from minus t0 to t0, x of t e to the minus j k omega naught t dt, plus the integral from t0. Let's bring it just down a little bit. So the integral from t0 to t over 2 x of t e to the minus j k omega naught t dt. Right. In this interval from minus t over 2 to t0, x of t is 0. So this is 0. And in the interval from t0 to t over 2, t0 to t over 2, x of t is 0. So this integral goes away. And I'm left with just this middle integral, which is the integral from minus t0 to t0. And in this interval, I still have the 1 over t out here. In this interval, x of t is just equal to 1. So in here, x of t is 1. So this becomes just e to the minus j k omega naught t dt. Right? And after this is just a bunch of math. So let's do the bunch of math. So this is equal to, right? I'm going to do another simplification. Omega naught is just 2 pi over cap t, right? So I'm going to substitute that, and I'll take that minus sign inside. So I have 1 over jk 2 pi over. And the t's cancel out here. What I'll do now is I'll take 2j and put that inside. So now, and this, of course, you recognize right away because Euler, and this is equal to then sine of k omega naught t naught over k pi. Isn't that great? That now is the kth coefficient of my Fourier series expansion, which, if I put it all together, will give me back my square wave. Okay, and I'll actually show you this. So ak was equal to sine k omega naught t naught over k pi. Okay. If I plug in k equals 0, we have a slight problem. Because if I plug in k equals 0, the denominator becomes 0. But thankfully, so does the numerator, right? Because we'll have sine of 0, and sine of 0 is just 0. So we have a 0 over 0 form. Whenever you have a 0 over 0 form, what you need to do is use L'Hopital's rule. And I know you might have learned about L'Hopital's rule in terms of limits. The idea still works when you're trying to evaluate something. You can think of the limit as k approaches 0. So in order to use L'Hopital's rule, the way you do that is you take the derivative of the numerator and you take the derivative of the denominator, and then you evaluate it at whatever value it is that was giving you problems before. And you can always only use that when you have this 0 over 0 form, right? So we're going to look for, what we're trying to do is find what a0 is in this case. And so if I take the derivative of the numerator, the derivative of a sine is a cosine, and I'm taking the derivative with respect to k. So this will be omega naught t naught cosine of k omega naught, k omega naught t naught. And the denominator is just pi, right? The derivative of k pi is just pi. And then evaluate this at k equals 0. So now cosine of k, cosine of 0 is just 1, and we'll get omega naught t naught over pi. And omega naught we know is 2 pi over cap t. So this is equal to 2 pi over cap t times t naught divided by pi. The pi's will cancel out, and we'll get 2 t naught over t. So depending on the pulse width, we'll get a different value for what a sub 0 is. Okay, let me take it just a few minutes, and then we can find what a1 is and a2 is and all that kind of stuff. let me just take a few minutes and talk about what A0 is. So instead of writing this generic form, remember, let's write the generic form first, and then I'll write the specific form. The generic form was a sub k is x of t e to the minus j k omega naught t dt integral over 1 period, right? A sub 0, if I substitute instead of a sub k, if I write a sub 0, then a sub 0 is equal to 1 over t integral over 1 period of x of t. And now here, instead of e to the minus jk omega naught t, I'll just get e to the power 0, which is just 1. So it's just that. Right? So it's the integral over a period divided by the period. That is the average value of the function, right? It tells you I'm taking one period, I'm finding the integral over that period, and then I'm dividing by that period. Think of the integral as a sum, and in that case you would have, if you took the sum over an interval and then divided by the size of that interval, you would have the average of that function over that interval. So a sub 0 then is simply the average of x of t over a period. Now the average over a period is the DC value of the signal, right? And if you remember, the signal that we're looking at is this. So what we're doing is we're taking the area of this and dividing by the size of the period, and that's giving us the DC value. Now you can see that if I take a larger, if T0 is large, so this is broader, we'll get a larger DC value. If this is a narrower pulse, we'll get a smaller DC value. And that is reflected in this thing here, in the coefficient. If as T0 becomes larger, A sub 0 becomes larger. The DC coefficient becomes larger. As T0 becomes smaller, A sub 0 becomes smaller. Okay. What about if I take this and I shift it down? So instead of doing this, what if I have something like this? So the way I've drawn it, if I took the average value now from here to here, and if this area here was equal to this area here, then the average value would turn out to be 0. Okay? And this would give me a situation where the DC coefficient is 0. A0 will be 0. The DC value is 0. I don't know what scopes you're using, but you have this on the scope, you have block DC. When you block the DC, you'll get, you're basically getting rid of A0 or setting A0 to be equal to 0. And if you have a signal like this in your scope, you'll see that it moves down. Right? So A0 is the DC coefficient. What about the other coefficients? Well, we can find those. Let's take A1. So that will be equal to sine of omega naught T naught over K pi. And now let's take a value for T naught, because otherwise we can't get so many numbers here. So let's take, what should we take? Let's take T naught to be equal to a quarter of the period. Right, so from minus T naught to T naught is half of the period. Okay, so if I do that, then A1 is equal to sine of 2 pi over cap T times T over 4 divided by, or let's just do generic A sub K. So that'll be K times, so this will be K pi. T's will cancel out. The 2 goes into here 2 times. So A sub K would now be sine of K pi over 2 divided by K pi. right? So a1, we can see from here, would be sine of pi over 2, which is 1, divided by pi. So a1 would be 1 over pi. A2 would be sine of 2 times pi over 2. So that's sine of pi. Sine of pi is 0. So a2 is 0. A3 is equal to sine of 3 pi over 2. 3 pi over 2 is minus 1, right? So pi over 2, 3 pi over 2 is minus 1. So this is minus 1 over 3 pi. If you go the other way, remember that this summation is from minus infinity to infinity. So what about the negative subscripted coefficients? A sub minus 1 is equal to sine of minus pi over 2. Sine of minus pi over 2 is minus 1 divided by minus pi. So this will be minus 1 over minus pi, or 1 over pi. A2 is sine of, or a sub minus 2 is sine of minus pi, which is 0. So this is 0. A3 is sine of minus 3 pi over 2. So that's 1 divided by minus 3 pi. So this is minus 1 over 3 pi. So you'll notice that, let's say a sub minus 3. A sub 3 is equal to a sub minus 3. A sub 2 is equal to a sub minus 2. A sub 1 is equal to a sub minus 1. And in fact, if you look at this thing, sine is an odd function. K pi is an odd function. Remember the definitions of even and odd that we had before. And odd works like minus and even works like plus. So I've got a minus divided by a minus, I'll get a plus, right? So if I have an odd function over an odd function, I get an even function. Okay, so this is two odd functions will give me an even function. So a sub k is an even function of k. Okay, I'm going to stop there, and I'm going to start the next module from exactly this place. So we'll start with, actually what I'm going to do is demonstrate to you that this particular expansion does actually give you back the square wave that we originally started with. Okay, and then we'll do just a few more examples in the next video, and then we'll move on to Fourier transforms. Okay, until then.